mes étudiants, ceci est la dernière conférence de cette semaine. Um, okay, back to English. Um, Today is the last lecture for this week, and we're going to finish chapter 6, and we're going to move on a little bit and start talking about chapter number 5. Last time I got interrupted by a friend knocking on the door, and I had to talk to my friend. Anyway, so we were talking about fault metamorphism. When you have faults, we talked about what faults were last time. Faults occur due to stress in the earth, and let me show you real quick again. First of all, when you get a crack in a rock, what do we call that? Anybody know? A crack in a rock. Let's play charades here. It's a joint. See there, and I don't recommend it. I don't do that anymore. But here's a crack in the rock. That's a joint. And when the rocks move on both sides of that joint, then we call it a fault. And faults are caused by stress within the earth. And stress forms from pressure. So bottom line is, you want to remember when you have faults, you could have metamorphic rocks because pressure is added, and it can produce foliation. Of all the different types of metamorphism that we've talked about so far, burial metamorphism involves primarily pressure. Regional metamorphism involves pressure and temperature. Subduction is also regional. Fault metamorphism involves pressure. All of those types of metamorphism can produce foliation, because foliation requires an increase in pressure within the earth. The only type of metamorphism that we've talked about that does not produce foliation is contact metamorphism, because pressure is not involved, just temperature is involved. So here you can see some beautiful foliation produced at a fault, and it's produced a gneiss. But this we call a myelinite is a special type of gneiss that's formed by fault metamorphism. So, last type of metamorphism we're going to talk about is called shock metamorphism. I think this one's one of the most interesting ones. I don't know if you've studied geology before, but 65 million years ago, a big asteroid struck our planet, wiping out the dinosaurs. If you took historical geology, we talked about it. Well, when an asteroid or a meteorite strikes our planet, it makes a big crater in the ground, and it produces a special type of metamorphism called shock metamorphism. So shock metamorphism is caused by extraterrestrial impacts. That means an asteroid or a meteor, or in rare circumstances, a comet. If it hits our planet, it can cause a special type of metamorphism, and it produces this very strange looking mineral here called shocked quartz. S-H-O-C-K-E-D. Shocked quartz. Normal quartz looks like this. This is normal quartz under a microscope. Notice when you take a quartz crystal and you put it on a microscope slide, you cut the rock so thin that light will pass through it, you get all these gray colors. 50 Shades of Gray. But look at the shocked quartz. It's got these brilliant colors in it, and it's got these lines in it. And the only way you can get shocked quartz, ladies and gentlemen, is through an extraterrestrial impact. That means an asteroid, a meteorite, or a comet. And there's one man-made way, through an atomic bomb explosion. That's how much energy is required to make shocked quartz. Shocked quartz, please don't forget, is related to shock metamorphism, and And when we find that, that's special. Usually we'll find it in a crater that's left behind by the object that struck our planet. That's a special type of metamorphism, and that involves the application of a huge amount of energy, a huge amount of pressure instantaneously, shocking the quartz. And when you find shocked quartz, not only do you know that it was from an extraterrestrial impact, unless there was an atomic bomb dropped there, you also get these tectites, Tektits. And these are little blobs of glass. Inside of this is hollow. And so when the meteorite strikes the planet, it makes a crater, makes the shock quartz, and it liquefies all the surrounding rock into glass, and then it moves out in all directions from the center of the crater. So tectites are also associated with shock metamorphism. Last thing in this chapter is identifying metamorphic rocks. Please take a look at that before you do your metamorphic rocks lab. What I wanted to do today is get you started on chapter number 5. So we've had a whole chapter on igneous rocks. We had a whole chapter on metamorphic rocks. And now we're going to have a whole chapter on sedimentary rocks. All of these chapter 4, 5, and 6 will be on the next test, and chapter 7 will be on the next test. And when is the next test? The next test is going to be on, let's see, should we do it on the 24th? If we do it on the 24th one, then it'll be the next test is going to be on 14, 28. The next test is going to be on, not next week. It'll be, so 15, 22, 29. It'll be not this coming Monday, but the Monday after that. So we'll have covered chapters 4, 5, and 6, and 7 for the next test. Maybe we'll get a little bit into 8. I'm not sure. But it won't be next week. It'll be the Monday after that. So let's take a look at chapter 5, Sedimentary Rocks. And the chapter is called Weathering, Erosion, and Sedimentary Rocks. I think, personally, of the 3 kinds of rocks, and rocks are not made the same thing as minerals. Rocks are made up of different kinds of minerals. I think sedimentary rocks are the most interesting. And I'm going to show you why. Sedimentary rocks are the only rocks that have fossils in them, evidence of past life. So the record of life on planet Earth is recorded in sedimentary rocks. That's one of the main reasons I love studying sedimentary rocks. I love going hiking with my dog, looking for sedimentary rocks. When my daughter was little, I used to go hunting with fossils to look for all around here in East Tennessee. My daughter and I collected hundreds of fossils. When I first moved here, this is after I got divorced to my first wife. My kids would come here, and my daughter would love to go fossil hunting with me. And we'd search through sedimentary rocks to look for fossils. And I'd tell her, "Would you rather live with Daddy? Look how much fun it is living with Daddy. We can go search for fossils. We can look at different types of rocks and study Earth history and climb mountains and go hiking. What do you get from living with your mom? You get to shop for handbags and shoes. That's not interesting." Anyway, I tried that argument. So But weathering, erosion, and sedimentary rocks. What is weathering? Well, weathering means breaking down rocks. So if you everything wears down with time, everything. The A tall mountain over time is going to be worn down to a flat plain. It just takes enough time. Rocks break down over time, and the way weathering is refers to the way they break down. They break down through either through many processes, either physically or chemically, and we'll talk about that. What does the word erosion mean? Erosion involves two things. It involves weathering, which is the breaking down of the rocks, but also carrying that debris. That so let's say you have a big rock and it's broken down into gravel, sand, and silt and clay, into sediments. Erosion involves both the weathering, the breaking down of that rock, and the carrying away of that sediment by water, wind, or ice. In this part of the country, it's primarily water that carries away the sediment. But up in Canada, it's ice. And out in Arizona, in the desert, it's going to be wind that's more important in moving the sediment. So a rock, solid rock like you see here, it's going to get broken down by the elements, either physically or chemically. And then it's going to be eroded. It's going to be carried away some other place. And then that sediment is going to get deposited into layers. And those layers we call beds. So looking at this beautiful vista here from Utah, western Utah. I don't know if you've ever been there. It's really beautiful. And you can't see stuff like this back east. A geologist standing all the way out here, thousands of feet away from this mountain, can say, these must be sedimentary rocks. Because I could see the beds, the layering. I could see these sedimentary beds. And when I think about these sedimentary beds, I get excited because I know that these layers down here are older than the ones that are laid down on top of them. So that the youngest beds are up here and the oldest beds are down here. Think about it, that has to be the case. These beds had to be laid down in order to form a surface upon which these beds could be deposited. And then these beds are deposited, and then these beds are deposited. And these sedimentary rocks are formed in deposited in different environments, in lakes or rivers or oceans or swamps. And so we could see how this part of western Utah has changed, going back into the past and moving up in time. And then we can look for fossils in these rocks, and maybe we'll be able to figure out how old these rocks were. And let's say we found out that these are limestones, and we find fossils in them indicating that these rocks down here were formed 380 to 440 million years ago. Well, that's interesting. If these are limestones with marine creatures in them, that means this part of western Utah was covered by the ocean 380 to 440 million years ago. Now let's say we find some sandstones here that were deposited by a river. That means that sea level fell and the land was exposed, allowing for rivers to deposit beds of sand. And let's say we find more limestone here. That means sea level rose, covering up those rivers. And let's say we find lake deposits here. That means that sea level fell, and then the land was exposed, and then you had lakes deposit this sediment. And then we try to read the geologic record from further back in time to younger and younger rocks. And then we could tell the history of western Utah. That's why I love sedimentary rocks. I don't know who your favorite author is. I like Stephen King, and when I read his novels, I love figuring out how his mind works and how the story works. But this is a real story here. This is probably the most interesting story you can imagine. You can read geologic time by looking at these outcrops. That means exposures of rocks. And if we could do this for western Utah, if we could do this for eastern Tennessee and southern New Jersey and Queensland in Australia and Honshu Island in Japan and Kamchatka in Russia, and we could record geologic history for let's say from 380 to 420 million years ago in all of these locations around the planet, can't we figure out what our planet was like 380 to 420 million years ago? And then if we do that with younger and younger and younger and younger rocks, can't we see how the Earth changed over time? That's why sedimentary rocks are interesting, because they record Earth history. 2 chapters from now, we'll be talking a little bit about Earth history. But if you're really interested in Earth history, take my other class, Historical Geology, where we talk about what happened in Earth's past. The other reason I love sedimentary rocks is because, and many geologists love sedimentary rocks, is because you can make money out of studying sedimentary rocks. Sedimentary rocks are the only rocks that have fossil fuels in them. Fossil fuels include oil, natural gas, and coal, all of which are essential to our economy. Every time you put gas in your gas tank for your car, you're putting the liquefied remains of creatures that have died millions of years ago into your car. That's why we call them fossil fuels. Creatures died millions and hundreds of millions of years ago. They can also make natural gas, or they also could get preserved in solid sedimentary rock, which we call bituminous coal. Don't forget, bituminous coal and anthracite coal are different. Bituminous coal is sedimentary. Anthracite coal is metamorphic. And if you get coal on your lab quiz, you need to know the difference between the two. Let's start off talking about weathering. There's two ways in which we can weather rocks or break them down. We can do mechanical weathering, which means we physically break down the rocks, or we can do chemical weathering. I'll write them down so that you have a list. It'll make it easier for you to study for this. So mechanical weathering means you physically break down rocks into small pieces, which we call sediment. They could be gravel, sand, silt, or clay sized. And mechanical weathering includes the following types: frost wedging, thermal expansion, exfoliation, which we also call unloading, salt crystal growth, and the fifth type of mechanical weathering is biological activity. There's 2 kinds of chemical weathering we're going to talk about. The main 2 types are acid dissolution and oxidation. Now, there's no way to talk about chemical weathering without talking about some basic chemistry. So I'm going to talk to you a little bit about that later on, and probably not in this video, because we're about done for this week. But let's first talk about mechanical weathering, which is how do we physically break down rocks into sediment. Well, one common way of doing it is called frost wedging. Frost wedging. Okay, when you look at a solid rock like this rock here from Canada, it's been broken apart. How did this rock get broken apart into these pieces like this? Well, it did so from frost wedging. You have joints in the rock, which are cracks. Then water gets into those cracks. What what happens when you freeze water? Does water expand or contract? Well, that's pretty easy. If you take a bottle, a glass bottle, and you fill it with water and you put it in your freezer, what's going to happen to that bottle? It's going to break apart, right? Well, the same thing happens with frost wedging. The water gets into the cracks of the rock, and then when it gets cold enough, it freezes and it tears apart the rock. It tears it apart. Frost wedging can break apart rocks. It can mechanically weather rocks. And where do you think frost wedging is going to be more important? Up north or down south? Up north, especially in Canada or the upper Midwest. Do you ever wonder why when you go up north of the Mason-Dixon line, there's toll roads up there when you go to New Jersey, Pennsylvania. When you go up there, why are there toll roads up there and there are no toll roads down south? That's real easy to explain. If you go to New York City or Boston or places like that, you got to pay high toll. The reason why is because frost wedging tears up the roads up north. You get potholes and cracks in the road, and the road department has to go and fill that in with asphalt. And then next year the road opens up again. It's a lot more expensive to maintain the roads in northern climates because of this frost wedging. Down south we don't have as much cold weather, and therefore there's less of a frost wedging problem. Well, the same thing happens with rocks. Next thing we're going to talk about is thermal expansion. Okay, now I want you to imagine something else. Thermal expansion. Imagine rocks not in a colder climate exposed to frost wedging, but in the desert in Nevada. Have you ever been to Las Vegas, besides the casinos, and gone out into the desert? Well, imagine there's a rock in the desert. And during the day, it gets up to 105 degrees Fahrenheit. Do you think the rock is going to expand due to being heated? Yeah, the rock will expand as it's heated in the desert. This rock is going to expand due to being heated in the desert. And then at night, it goes down to a chilly 50 or 40 degrees. Then that rock is going to contract. Every day, that rock is going to expand and contract due to the huge difference in temperature between night and day. That will literally tear apart the rocks. And that process of mechanical weathering is called thermal expansion. So we're going to call it quits for this week. That's all you need to watch for this week, and I'll continue this on next week. I hope you all have a wonderful week.